Hello all, welcome to video 1 from section 1.9, the matrix of a linear transformation. So a transformation is just any function that has input a vector and assigns to that vector some other vector. Our big example so far is taking a vector x and then assigning it the vector ax for some matrix A. We saw last time that all these transformations are linear, which means they split up nicely over sums, and they split up nicely over scalar multiplication. So in this section, we're going to show that, what are we actually going to show that? We're going to show that, but I have misplaced my notes. We're going to show that, every linear transformation comes from the matrix. Every linear transformation comes from a matrix. Okay, so we saw last time that all these transformations that come from matrices have this nice linear property. This time we're showing that, well, actually, that linear property is enough to force the transformation to be of the form x gets mapped to ax. Okay, and a quick note, this matrix I, which has ones, in the 1-1 slot and the 2-2 slot, the 3-3 slot all the way across this diagonal, is called the identity matrix. Its columns are at the first column. E1 has a 1 in the first column and zeros elsewhere. E2 is a 2 in the second slot and zeros elsewhere. In general, the ith column of this matrix has zeros everywhere except for a 1 in the ith spot. And you can check that this matrix has the nice property that if you matrix multiply it with any vector, you get back the same vector again. So it acts like the number 1 does for regular multiplication. Okay, we have this theorem 10 that says if we let T be some linear transformation from Rn to Rm, then there is a unique matrix A such that what? The thing we want is true. If we apply our linear transformation T to x, it's actually equal to ax, and this is true for all vectors x in Rn. And even better, this just says, some matrix A exists. Even better is that we can tell you how to find that matrix. So as well, A is the matrix you get where if you apply T to each of the columns of your identity matrix, those become your columns of the matrix A. So the first column of A is T applied to E1. The second column of A is T applied to E2. The last column of A is T applied to En. So in other words, the jth column of A is T applied to EJ. Okay, and we say, what do we say? We see T either corresponds or represents A. T corresponds to A, or maybe you say represents, depending on who you're talking to. Or sorry, not represents, is represented by A, or you can say A is the standard matrix for T. A is the standard matrix for T. And if you're wondering if there are other matrix representatives of T, like non-standard ones, the answer is yes. We'll see those, if not in the end of 341, then certainly at the beginning of 342. All right. Let's look at an example. So let's look at a few examples, I think. Let's consider T from R2 to R2. And we want the transformation that just rotates each vector counterclockwise by pi over 2 radians. Rotates each vector counterclockwise by pi over 2 radians. Okay, I don't think we've shown this is linear. I think the book says that it is, and the book maybe goes through that argument too. But for now, we're going to just say, assuming this transformation is linear, what must its matrix be? So assuming this transformation is linear, yeah, what matrix must represent T? Okay, so oops. Oh, here we go. I'm sorry, I've wasted your time. Okay, consider this matrix. It rotates by pi over 2 radians. Assuming the transformation is linear, what matrix must represent T? Yeah, so theorem 10 says, remember this theorem? Theorem 10, good. Theorem 10 says, here's our solution. It says as soon as we know where the vectors 1, 0, and 0, 1 go, we've captured all of the complexity of the linear transformation. If we know where E1 goes and where E2 goes, then we know A. Okay, so let's draw a little picture and see what's going on here. Here's our copy of R2. It's the X1 axis. There's our X2 axis. E1 is the vector like so. And if it's being rotated by 90 degrees, oh, there it goes. It gets mapped to do a different color. It gets mapped to E2 actually. So we can see here that T of E1 is E2. And what happens to E2? Let's do get another axis here so we're not getting confused with the pictures. So there's our copy of E2. If it's being rotated 90 degrees, it's going right over here, which looks like negative E1. Okay, so we're getting that T of E2 is negative E1. And so A, the matrix representing this transformation, has to have columns E2, negative E1. We know exactly what that looks like. We know E2 is 0, 1. We know negative E1 is negative 1, 0. And sure enough, this is the matrix that rotates every point in the plane by 90 degrees. Check it out if you don't believe me. So for fun, check, the vector 1, 1 is rotated by 90 degrees. Or pi over 2 radians, whatever. Okay. And there's nothing special here about pi over 2. You could do any rotation. In fact, I'm pretty sure the textbook goes over an arbitrary rotation, theta, instead of a concrete one. So you're encouraged to take a look at the textbook to see more examples. Let's do another example. Here we go. We've got a transformation T from R3 to R3 that doubles the length of any vector. And we saw this last time in dilations. Yeah, so we do know this one is linear. We want to know what matrix represents T. So again, we can play the same game. If we know what E1 goes to, and now we need to worry about E1, E2, and E3 because we're working in R3. But if we know where E1, 2, and 3 go, then we know the entire matrix. So we know E1 goes to twice E1. We know E2 goes to twice E2. Okay, this is getting, we know E3 goes to twice E3. So we know what A is. A is just the matrix whose columns are twice E1, twice E2, twice E3. And we can write down concretely what that matrix is: 2, 0, 0, 0, 2, 0, 0, 0, 2. We can check, yeah, so this is A, and T of X is equal to AX for all X. That's the claim from theorem 10. Should have said that up here too. Oh. So for all X in R2. Okay, at some point during the pandemic, I started writing happy faces all over the mathematics that I do. It's the way it goes. Okay. Boom. One more example. Yeah, okay. We want to determine the matrix representing the transformation from R2 to R2 that reflects vectors along the X1 axis. Here, we'll have to check that, we'll have to assume this is linear again, but that's okay. So what I mean by reflecting, let's make sure we understand the assignment. We've got our axes here. A reflection along this is our X1 axis. It's our X2 axis. If we're reflecting along the X1 axis, it means that if we grab a vector like so, yeah, we just want to take the mirror image. So this will be like that. That's T of X. Okay. So again, all we're going to do is apply the linear transformation to E1 and E2, squish those together into a matrix. Boom. That's the matrix for the linear transformation. So if we reflect 1, 0, this vector right here along the X1 axis, what happens? Absolutely nothing. It gets sent to itself. Boom. E1 is mapped to E1. If we take E2, where does it get mapped to? That's the vector right here. And if we reflect, we get the same vector in the opposite direction. So E2 is being mapped to 0, -1. Okay, so we know that T of X is equal to what? 1, 0, 0, -1. X for all X in R3, R2. Okay, should we do one more longish example? Yes, here it is. Okay, we want to define a transformation T. It should be T from R2 to R2. Transformation T that rotates each vector counterclockwise by pi/3 radians and then reflects across the X2 axis. Okay, so again, assuming this transformation is linear, let's find the standard matrix for T. This is more complicated, but it's not any more difficult for us because all we need to do is check where does 0, 1 get mapped to. As before. Just need to find where E1 and E2 are sent. Okay, so 1, 0, 0 rotates. Here we're going to need to use our unit circle. So I hope you all haven't forgotten that yet. Okay, I don't know how you remember it, but I remember it like this. I not left myself room to write this down properly. Let's try again. Okay. Oh, we know the middle one is easy. It's root 2 over 2. Root 2 over 2. We've got a 1 over 2 and a root 3 over 2. This one is farther out, and I know root 3 over 2 is bigger than 1 over 2. So this has to be root 3 over 2 and a half. And that means this has to be a half root 3 over 2. Okay. So if we rotate 1, 0 by pi over 3, so we're going from here to there. So it looks like what we're going to get is this gets matched to 1/2 root 3 over 2. That's the rotation, and then it's going to get reflected to. So this is rotation. This is the reflection. And if we reflect it down, well, it gets taken to what? The x value stays the same and the y value picks up a negative sign. So this goes to x is the same and the y value picks up a negative sign. So this is where E1 gets mapped to. Oh, I'm sorry, we're reflecting to the x2 axis. Sorry. Let's try this again. What does that actually change? So we're reflecting over x2, x1. We're reflecting over here now. So same idea. The height stays the same, and the x1 just gets negated. So this should be negative 1/2 root 3 over 2. We need 2 will be similar. 0, 1. So that's like right here. Now we're going to rotate this pi over 3, so it becomes over there. So this is just what? This should be negative root 3 over 2, 1/2, since we're on the opposite side. So this will be negative root 3 over 2, 1/2. Oops. And then, so it's rotated from there to there. And then when we reflect, it'll come back over here. So this is the rotation. This is the reflection. Okay, so then our matrix is just these things grouped together into a single matrix. Negative 1/2 root 3 over 2, root 3 over 2, 1/2. Okay, and then we know that actually our linear transformation is just equal to AX for all x. Okay, and we've done examples in R2 and R3. There's no reason we can't do an example from R2 to R3 or R3 to R2 or Rn to Rm. The process is all exactly the same. All right, I'll see y'all in a sec for the next installment from section 1.9.